So let's say we have a reaction, A and B are reactants, C and D are products, and the rate law is provided as the rate constant, K, times the concentration of A squared times the concentration of B. From this rate law, we can complete the blanks in this bullet point here. First one is the rate is some order with respect to A and what order with respect to B. Well, the coefficient tells us what that order is. So, not the coefficient, the exponent. So the exponent for A is 2, so the rate is second order with respect to A. And B is included in the rate law, so it has an exponent of 1. We usually don't write the exponent of 1, but if that reactant is included in the rate law, then you can assume that coefficient is 1, and it is first order with respect to B. If something had a 0 order, like if B was 0 order, it just would not be part of the rate law, but you would still know it's a reactant based on the chemical equation. Okay, now second bullet point, or third, I guess. At a certain concentration of A and B, the reaction has an initial rate of 0.320 molarity per second. Calculate the new initial rate when the concentration of A is tripled and the concentration of B is doubled. So, for this question here, we have to consider the rate order for each reactant and the result of tripling the concentration of one and doubling the concentration of another. If we triple the concentration of A, so instead of A in this equation, we have 3A. Well, that 3 is squared, so this actually increases the reaction rate by 3 squared, which is 9. So this is concentration of A is tripled. This is the result of that. If we double concentration of B, that increases the rate by 2, because we're doubling, raised to the power of 1, because the reaction is first order with respect to B. So increases reaction rate by a factor of 2. We multiply in the reaction rate, we multiply A and B together, so the overall rate reaction rate increases by a factor of 9 times 2, which is 18. Another way to write this is to have a ratio where we have new rate to old rate. We have the same rate law, so let's write the old rate first. K, concentration of A squared, concentration of B. And then the new rate, we have 3 times the concentration of A squared times 2 times the concentration of B. We can cancel everything out except for 3 squared times 2, which is 18 over 1. So 18 times the original rate. So new rate is 18 times the old rate So 18 times 0.320 molarity per second. The new rate is 5.76 molarity per second. So both increasing concentration of A and B increases the reaction rate, and it depends on the rate law to determine how this exactly impacts the reaction rate. All right, I will end this video here and we'll do more examples in the next video for chapter 14. All right, hello. I'm going to start this video with where I left off in the last one. So we did this learning check where we were provided the rate law for a reaction that had reactants A and B. The rate was the rate constant K times the concentration of A squared times concentration of B. So we could tell from that rate law that the rate is second order with respect to A, first order with respect to B. And what happens when you increase the temperature, when you increase the concentration of A, that would increase by a rate of whatever that increase is. So we said tripled squared. So 3 to the power of 2. If something is first order, then if you double or triple its concentration, you would double or triple its rate, that reaction rate. Now in the next couple of slides, we're going to determine what this rate law is. So this rate law for different reactions based on concentration data at different experiments. So we could tell if we doubled B and the reaction rate doubled, the reaction rate doubled, then we could tell exactly that the reaction was first order with respect to B. So we're going to go through this, and these would be scenarios where you're not provided the rate law, you don't know what that rate law is, but you have concentration of different reactants at different times and the rate at those times. So we have a reaction with two reactants, A and B, some coefficients, and we can like right away write this out where we know that the rate is the rate constant times the concentration of A to N, which is whatever the reaction order is with respect to A, times the concentration of B with whatever the reaction order is with respect to B. So using this experimental data here, we have different experiments and the initial rate with those experiments, we can determine the reaction order with respect to A, the reaction order with respect to B, and the rate constant. You need to know the reaction orders before you can calculate rate constant, so that's what we'll do. We'll calculate these reaction orders and then the rate constant. So to determine the reaction order with respect to any reagent, we have to find two sets of experimental data where the concentration of the reactant that we're interested in is the only thing that changes. So for A, we're looking for the reaction order with respect to A. In experiments 1 and 2, the concentration of A is doubled, the concentration of B stays the same. So any change in the initial rate of this reaction is a direct result of the concentration of A changing. So we can use experiments 1 and 2, and we'll find the ratios of these two experiments. We'll take the rate of 1 divided by the rate of 2, and that ratio will be equal to the equation, so rate constant times concentration of A at time, you know what, let's do 2 over 1. So rate 2 over 1, you could do it either way. This is how I have it in my notes, so just to avoid any mistakes in the video, I'm going to do 2 over 1. So this should be equal concentration of A to the power of N at time 2, not 1 there, times the concentration of B at time 2. And this is rate constant times the concentration of A to the power of N at time 1 times the concentration of B to the power of M at time 1. Well, the concentration of B is not changing when we go from experiment 1 to experiment 2. Oh, change the slide. All right. Pretend we're working on A here, and then we'll go back for B. So still work on your A slide. Okay, so we're working with experiment 1 and 2. The concentration of B is not changing. It's 0.0250 in both, so we can cancel those out. They're not changing. K is also not changing, so we can cancel that out. So rate 2 over rate 1 is equal to the concentration of A at time 2 to the power of N divided by the concentration of A at time 1 to the power of N. We're looking at the ratio of these rates, which again is directly related to the ratio of the concentrations. We can simplify this further since we're raising the numerator and the denominator to the power of N. We can bring that to the outside. Oh my gosh. N. Keep making mistakes here. Okay, so you can bring that to the outside of the fraction and put that fraction in parentheses, say the power to the N for both the numerator and the denominator. This is helpful for the next part. So getting to this, rate 2 over rate 1 equals concentration of A at time 2 divided by concentration of A at time 1, all of that raised to the power of N, which is the reaction order with respect to A. Now we'll plug in values. So rate 2 is 8.16 times 10 to the negative 3. Molarity per second. Rate 1 is 2.04 times 10 to the negative 3 molarity per second. This is equal to concentration of A for experiment 2, and this is 0.0500 molar divided by concentration of A for experiment 1, 0.0250 molar. All of this raised to the power of N. If you take the left side and divide, you will find that that left side is equal to 4. Inside the parentheses, if you do that division, this is equal to 2. So we have 4 equals 2 to the power of N. Now we have to think about which exponent, when applied to the value 2, gives you 4. Well, 2 squared is 4. So N is equal to 2. And this tells us the reaction, Rxn, short for reaction, is second order with respect to WRT with respect to reagent A. So at this point we can say that the rate is equal to rate constant times the concentration of A squared times the concentration of B to the power of M. We still need to find that reaction order with respect to B. Now we do another calculation to find the reaction order with respect to B. When finding experiments to determine the reaction order with respect to B, we want to make sure that the concentration of B is the only thing changing. The concentration of A is not changing. So looking at the table, we can use experiments 2 and 3. Concentration of A remains at 0.05. Concentration of B starts at 0.025, and in experiment 3, it's 0.05. So we'll do the same process. We'll take the rate of experiment 3 divided by the rate of experiment 2. This is equal to, I'm going to simplify this here, concentration of B for experiment 3 divided by concentration of B in experiment 2, all of this raised to the power of m. We can go through the same process as this slide where we wrote out the full rate law. So rate 2 is equal to K times concentration for experiment 2 times concentration for experiment 2. Cancel out what is present in both the numerator and denominator here, and then we get this final fraction with the exponent n. So that's what I did. That's the process to get to this fraction here with the exponent m. You can certainly write that out to convince yourself that we can make that leap. Now we can plug in values. So the rate of experiment 3, 1.63 times 10 to the negative second molarity per second. And then rate 2, 8.16 times 10 to the negative third molarity per second. This is equal to concentration at experiment 3 divided by concentration at experiment 2 to the power of m. Simplifying both sides, the left side is equal to 2. The fraction on the right side is equal to 2, so power of m. Now we think which exponent raised 2 raised to which exponent would equal 2. That would be if m, that exponent, equals 1. So this tells us reaction is first order with respect to B. So now we can write out the rate law. Rate is equal to rate constant times the concentration of A squared. That was the previous calculation. We found it second order with respect to A, times the concentration of B to the first power, but we usually just don't write that one, so we would leave that blank. So this is our rate law. We've got the equation. Now we can use that to determine K, the rate constant. So let's rewrite out the rate equation. So we have the rate law. We can use any one of these experiments, 1, 2, 3, or 4, plug in concentration of A, concentration of B, and the rate, and then all we're left with is to solve for K. Let's rearrange this equation. So rate divided by concentration of A squared times concentration of B, this is equal to K. And then we can use values from any one row or one experiment. Let's do experiment 1. It shouldn't matter. You should be able to use any row and you'll get the same K value. So experiment 1, the rate is 2.04 times 10 to the negative third molarity per second. Concentration of A is 0.0250 squared. Don't forget to square it. Concentration of B is also 0.0250 molar. Let me get units in here for concentration of A. Now, if you have a habit of leaving out units, I highly recommend that you definitely leave them in for these types of equations, because you need to consider how the units are in the fraction to find the units for K. The units for K can change depending on the order of the reaction. So all of this is equal to K. If we simplify the values on the right side, or on the left side, this is 130.56. Now we have to think about units. We have molarity, the top. We have molarity cubed in the denominator. This right here gives us molarity squared, and then times another molarity, so that results in molarity cubed. I will use green for units. So we have molarity per second over molarity cubed. When you have a unit on the top and the bottom of a denominator of a fraction, the exponent will cancel out. You subtract one from the other. We have more molarity units on the bottom, cubed on the bottom, one on the top. So that means that we will have molarity squared on the bottom and no molarity at the top. That got canceled out. And then we also have that per second at the top, which we can move into the denominator. Another way to think about this, I'll do this in the top right corner. So if we have molarity per second divided by molarity cubed, this is equal to molarity times second to the negative first power times molarity to the negative third power. That negative, if you keep it in the numerator, like all of this would be over 1. So if you move anything in the denominator to the numerator, you raise it to a negative power. So now we can simplify. This is seconds to the negative first power times molarity to the negative second power over 1, or 1 over second squared. No, not second squared. 1 over second times molarity squared. These are equivalent. So back to our rate constant. 130.56 molarity to the negative second power times seconds. That is equal to K. So our rate is equal to 131. We'll change the number of significant digits. You can keep it the same. I'm not doing that for any specific reason, just to simplify. So the rate is 131 per molarity squared per second squared times the concentration of A squared times the concentration of B. And we got that whole equation based on these experimental data. But these are example reaction orders and rate laws for different types of reactions. So if we have a reaction that's 0 order, an example rate law, so we're looking at this first row here, an example rate law would be K to reactant to the 0 power, which would actually just be K. And in that case, the units of K would be meters per second or meters times second to the negative first power. If you have a overall reaction order of 1, there are different units of K, and then if you look down that column, you'll see that there are different units depending on if you have a different reaction order. The units are there to align with concentration units for whatever is present to make sure that the rate unit, so the rate is always molarity per second. So let's do, the next few slides are this learning check, and I'm going to go through them, but you should try to do this on your own, or maybe watch a little bit to get started and then try to work through it on your own. This is similar to the learning check that was just done. We just have a different reaction. We've got real reagents and products, and we're going to find rate law, rate constant, and then determine the rate for certain concentrations. So nitrogen dioxide is a component of photochemical smog that is in the air. This forms according to this equation. We have nitrogen monoxide with oxygen gas that forms nitrogen dioxide. So we have some experimental rate data measured at constant temperature. It's provided in the table at the bottom of the slide. And we're going to determine rate law, K, and then rate for certain concentrations like I mentioned. So I have one slide to do kind of each of those because we'll need some space. So first we have determining the rate law. Well, we can write the rate equation, but we don't know exponents yet. But we know that the rate will be equal to some rate constant times the concentration of NO to some power. We have to figure out what that is, which we will do on this page. And then times the concentration of O2 to some power. Again, we'll find that on this page. To determine the order with respect to an individual reactant, we need to compare two sets of experimental data. So let's start with N. To find what N is, so the reaction order with respect to nitrogen monoxide, we need to find a set of experiments, so 2 rows, where the concentration of O2 stays the same but NO changes. That way we can determine how concentration of NO impacts the rate of the reaction. So we will take rate 2 and 3. We see here that NO, concentration of nitrogen monoxide, increases, but concentration of O2 stays the same. So any change in the initial rate is only because of the concentration of NO change. So we'll take rate 3 over rate 2. This is equal to the concentration of NO for experiment 3, that's what that subscript is, divided by the concentration of NO for experiment 2, raised to the power of N. We are using the rate law, but for that second fraction that I have in those larger parentheses, we can cancel out K, we can cancel out concentration of O2 because they do not change. So we're just simplifying to what does change in that rate law. You could put everything for reaction or experiment 2 in the numerator and experiment 3 in the denominator. You'll still get the same N value. I just chose to put 3 on top. So let's plug in some values here. So we have 1.8 times 10 to the negative 4 molarity per second divided by 4.4 times 10 to the negative 5th molarity per second. So these are just the rates of those two reactions. This is equal to concentration of NO for experiment 3, 0.0042 molar, divided by concentration for experiment 2, 0.0021 molar, raised to the power of N. The left side of this equation is equal to 4. On the right side, if you simplify that fraction, you'll get 2. So that is to the power of N. For the value of 2 raised to some exponent, the exponent that is needed to make that equal to 4 is 2. So N equals 2 here. 2 to the power of 2 is equal to 4. So when the concentration, in this case, when the concentration of NO doubles, the rate quadruples. That's what these two values tell us. When the concentration doubles, the rate quadruples, so N must equal 2. Okay. I'll use a different color here. Oops. To find M. So we have found N, we need to find M. This is the reaction order with respect to O2. Here we will use experiments 1 and 2, where concentration of NO stays the same, but concentration of O2 changes. All right, just setting up that equation so far. The ratio of the rates is equal to the ratio of the concentrations raised to some power. Plugging in values now. Okay, I've plugged in the rates and the concentrations of O2. Simplifying the fractions only, we get 1/2 is equal to 1/2 raised to the power of M. The value of M that would set the right and left side of that equation equal to each other is 1. So M is 1. So we can put the rate equation all together now. So rate is equal to K times the concentration of NO squared times the concentration of O2, and that is our rate law. I said something earlier, I want to write it down when we talk about N, for example, when the concentration of N2 doubled, NO doubled, the rate quadrupled, so that implies that the reaction order is 2. And then over here, when concentration of O2 is halved, rate is also halved. So M must equal 1. Okay, we've got our rate law. Let's go to the next part of this question, which is to calculate K. We're going to need that rate law, so I will rewrite that down. Okay, so what we found on the previous page. Now to find K, we can plug in information from any one of these experiments. I'll first rearrange this equation to solve for K. So that will be the rate divided by concentration of NO squared times concentration of O2. This is equal to K. So you can pick any experiment. I picked the first one. So the rate here is 8.8 times 10 to the negative 5th molarity per second divided by concentration of NO squared, so 0.0021 molarity squared. And and then concentration of O2, 0.0032 molar. And that is equal to K. Simplifying the fraction, I have, don't forget to apply this exponent here to the value as well as the unit. But the value of this fraction is 6.2 times 10 to the negative third. And then let's figure out what these units are. So we have, I'm just going to do this over on the side. We have molarity times seconds to the negative first power in the numerator. And then in the denominator, we have molarity squared times molarity again. So that's molarity to the third power. We get molarity squared here, and then times another molarity, so molarity cubed. So the units would have the molarity in the numerator cancels out with 1 in the denominator. So we have seconds to the negative first power over molarity squared, or we can write this as molarity to the negative second power and seconds to the negative first power. So those are our units for K. And there's our K value. Now let's go to this last question, or this last part of the learning check, where we are determining the rate of the reaction given certain concentrations that are not already part of the experimental data. So we need the full rate law again. And I'm going to, let's see, we've got K is times NO squared times concentration of O2. We know K from the previous slide. And then concentration of NO, 0.0015 molar, square that, times concentration of O2. And then if you simplify this equation and the units, you'll have 3.3 times 10 to the negative 5 molarity per second. And that is the rate when NO is this concentration, O2 is that concentration. Okay, so that concludes this learning check. So now that we've discussed how to find a rate law, this is useful when you have K or you have concentrations or you have this experimental data. We're going to move to integrated rate laws, which is used, it's another form of the rate law, so another equation that is used to predict concentration and time values of a reaction given these rate laws. Now, the integrated rate laws are the equations that are provided on your periodic table and equation sheet, and it lists if the rate law is for zero order, first order, or second order reactions. We'll also see how graphing data can help identify the order of a reaction, and then we'll talk about half-life. We've already kind of talked about what a first order and second order reactions are, but half-life will be new to us. So far, we've talked about how reaction rates decrease over time as the concentration of reactants decreases. This was the first section. We covered this in class, and we have seen it in a lot of the graphs that we've looked at so far in this chapter. This decrease in concentration depends on the order of the reaction. We talked about that as well. If you have a higher order, the decrease is more significant. So now we're going to learn how to use the integrated version of first and second order rate laws to predict the concentration of a reactant at any time, or to use the concentration to determine how much time has passed. So it integrates both concentration and time into one equation. And there are different equations for first and second order reactions. We'll talk about first order first. So, but we know some background info or reminder. We know that the decrease in reactant concentration for a first order reaction is not linear. So that's this blue line over here. Well, I just underlined first order. It's the blue line that's on there right now. That makes it difficult to predict the amount of reactant or the concentration of the reactant at a given time because it's not a linear graph. So this integrated rate law can be used to predict the concentration at a certain time, or if you know the concentration, how much time has passed. So the first order rate law, going back to section 1, if you have a reaction that is just reactant A forming product B, we could say that the rate is equal to the negative change in concentration of A over change in time. And this would also be equal to K, that rate constant, times the concentration of A. So we learned the left side of that equation in section 1 and the right side of that equation in sections 2 and 3, or actually in section 2. Rearranging and taking the natural log of one side gives us the integrated rate law. There are more steps to derive the integrated rate law, but I'm going to give it to you here. This is on your periodic table sheet. If you go to the book for this section, it goes through the derivation of this equation. But the integrated rate law for first order reaction, you take the natural log of the concentration of A at time t divided by the concentration of A at time 0. So that's the initial concentration. Let's write this over here. Concentration of A with subscript 0 is initial concentration of A when time is equal to 0. No time has passed. Concentration of A at time t is the concentration of A at some specified time. Where that time is t, so that would be given in a question, how much time has passed. This is equal to negative K times the time that you measure that concentration. So again, deriving this is explained in the book. My goal for you all is to be able to use this equation. It can be rearranged into a y equals mx plus b version. This can be helpful because that way plotting these variables would give a straight line. So the y equals mx plus b version is natural log of A at time t is equal to negative K times time plus natural log of A at time 0. So to break this down, concentration of A at time t will vary. It is a function of time. So this would be the y, if we're talking about y equals mx plus b, this would be y. Negative K is the slope, so that is m. T would be x, that is the x-axis, that's what will change as well. And then natural log of A at time 0, this is a constant for a given reaction, given concentration. That does not change with time. So there's the y equals mx plus b version. If you plot that, so going to the next slide, if you plot this time versus natural log of the concentration of A, that results in a straight line. Where the slope of this line is negative K, and we said that on the last slide. Before we do learning checks, I want to go through half-life of first order reactions. We'll do integrated rate law for second order, half-life of second order, and then we'll do some learning checks. So just more background information for now. So this is the integrated rate law for the first order reaction. Then let's talk about half-life for first order reactions. this is usually represented as T with the subscript 1/2. This is defined as the time it takes for 1/2 of the reactant to be used up. So looking at this graph, at time t equals 0, you have some amount of these reactants here. After 1 half-life, half of them are gone. So you started with 8, after 1 half-life, now there's only 4. After another half-life, there's 2. After another half-life, there's 1. But notice that the time, so for this example, the half-life is all 1 minute. Now, it's not always 1 minute, but the half-life is independent of the concentration. So this is something I'm going to write down here. It is independent of the initial concentration. No matter what concentration you start with, the half-life will be the same for a given reaction. Okay, so what I have on the left side here, we're going to go through a derivation of the integrated rate law to get to the half-life equation. So this is derivation. We're going to start with the integrated rate law, so the natural log of concentration of A at time t divided by concentration of A at time 0, so initial concentration, is equal to negative K times T. If you divide both sides by negative K, that would allow us to solve for T. We'd have 1 over K times the natural log of concentration of A at time 0 over concentration of A at time t. So I've switched that fraction, I'll explain why, and this is equal to the time. If you multiply natural log of a fraction by a negative number, that's equal to the natural log of the inverse. So I've inversed the fraction that we take the natural log of because we multiplied by negative K, or divided by negative K. Okay, so then when we're talking about half-life, the definition of concentration of A at times T is that it is 1/2 the concentration of A at time 0. So if we substitute that definition in, we get 1 over K times the natural log of concentration of A at time 0 over 1/2 concentration of A at time 0. And this is all equal to T. Again, we have that 1/2 concentration of A at time 0 because that's the definition of a half-life. It's the time when 1/2 of the initial concentration is left over. So now we can simplify, cancel out initial concentration, rearrange those fractions because we divide by 1/2, that's the same as multiplying by 2, and we would get natural log of 2 over K is equal to half-life. So few steps to derive this equation. What we'll be doing is mostly just applying this equation when you're given a half-life type of question. Okay, so we've talked about integrated rate law for first-order reactions, half-life for first-order reactions. Let's talk about second-order reactions. We could have 2 types of second-order rate laws. It could be in a situation where there is one reactant, but the reaction is second-order with respect to that single reactant. Or you could have where the rate is equal to K times the concentration of one reactant and the concentration of the other, and those are both first order with respect to each reaction, so overall the reaction is second order. When we're talking about integrated rate laws, we're focusing on this one. So we will focus on this rate law. When we're talking about the integrated rate law for second order reaction. Okay, again, we have where the rate is equal to negative change in concentration of reactant over change in time. And this is equal to K times the concentration of A squared. The integrated rate law, this is another situation where you can see the derivation in the book, but we'll just go straight to writing out the equation. The integrated rate law, also provided on your periodic table equation sheet, is 1 over A at time t, which is equal to K times T plus 1 over initial concentration of A. This is already in the y equals mx plus b version. So we have K is m, or the slope, T is x. Concentration of A at time t is a function of time, so this is the y. And then concentration of A at time 0, or initial concentration, is a constant that does not change with time, so that is our b. So if you plot 1 over A, concentration of A versus time, the slope will be K, the y-intercept is 1 over initial concentration. And then we got half-life here, so the half-life of a second order reaction, same definition, it's still the time it takes for 1/2 of the reactant to be used up. We just have a different equation here. In this case, that's right, the integrated rate law, again, we're deriving it. We're deriving the half-life equation, I should say. 1 over A at time t equals K times time plus 1 over concentration of A at time 0. If we substitute in the definition of concentration of A at time t, meaning that it is 1/2 the initial concentration and then rearrange and simplify, we have 1 over K times the concentration of A at time 0 is equal to the half-life for a second order reaction. Now this second order reaction, having the initial concentration as part of the equation means that half-life for a second order reaction does depend on both K and the initial concentration of A. And we know that because it is part of the equation. I'll scroll up a couple of slides here. The half-life for a first order reaction depends only on K. So we can write that down here. So that's for first order, scrolling down. All right, we will do this learning check. This will be in the next video, so I'll stop this one here.